Hi, I'm Eric Matzner. I've got a book called History of Nootropics, Plants to Piracetam. So this is a book that came about kind of organically, where I was doing a lot of research into the history of nootropics and just cognitive enhancers and the way that our brains evolved to make us smarter. And for those of you who don't know, nootropics is derived from the words the mind and toward, so it means towards the mind. So it itself came out organically when scientists were looking for a GABA-related sleep aid in the 1960s, but we'll get to that. So we're going to trace the evolution here. So we'll start with a quote from the founder of the nootropic concept, which his name is Cornelia Gurgia. He's a Hungarian neuropharmacologist who is at a lab in Belgium. And he basically says, humanity will not wait passively for millions of years until Mother Nature will hand it a functionally better brain. Basically, he's saying, we can't wait for evolution to enhance our brains. We have to take it into our own hands. And I mean, I'm at the Body Hacking Conference here with you guys, so you all know this. But most people seem to think that humans are passive in their evolution. And in some ways, historically, we have been. But we've been affected by the molecules around us and the things in our diet and what the environment's providing. And so we're going to look at how our brains, how we went from footprints on the savannah in the mud to moon footprints of boots in space. So how did our civilization go from apes to great escapes to the moon? So we're going to look at that. So evolution is in fits and spurts. It's not necessarily this linear thing that happens where you go straight into humanity. You could see there's many failed lineages around there, so I can't really look at these graphs. But and so this is also a longer talk adapted to the shorter time period. So this is something called symbolic cognition here, where you can see how human art skills evolved over time in the different millennia. And so you can see that something was going on, and so the magic molecule here is a molecule called DHA. So you may know this. It's a part of fish oil. You have DHA and EPA. This is one of the two fatty acid things you can't really get from the environment that enhances your brain. And there's a path that we're going to look at briefly that shows how humans eating fish potentially changed the course of our history. So these are ratios of body to brain weight. And you can see basically what happens is that in nature, there's not a lot of DHA available. And so, and especially in the savanna, in the grass, and so larger animals, they eat grass and their body mass and their caloric intake increases, and everything that they're eating, their body size increases, but their brain doesn't. So what changed with humans? And so part of this is that the world changed on us. And so basically, where we lived in Africa, these rift valleys came out and gave us a protected area and allowed us to come out of the trees, and also isolated us near lakes and streams and water, fresh marine ecosystems, as they call it in the text. And it's basically, we were eating a lot of fish suddenly. And so then we now have this molecule that was a limiting factor in the encephalization, which is the change in brain size. And so there's this, we all know survival of the fittest, but there's actually a much, in my opinion, somewhat more interesting aspect of evolution, which is called exaptation. It's talked about a lot less, but it is basically what happens in our evolutionary history when we have access, for example, to this DHA that grows our brain size, what comes from the increased brain size from an unrelated area. And so this exaptation led to the increase in our brain size. And so this is a quotient, I believe, of the different ratio of body to brain weight. And you can actually see that a baby has the greatest ratio in the entire planet. Because babies have a ton of fat. Fat is made of molecules like DHA. So we're going to look here at the lateralization of brains and a little bit of just how they change in growth size. And we're going to, on the two images on the left are baby, the one image on the left on the top is a baby. the next one's a 6-month-old, is a 1 month and a 6-month-old, and same thing on the bottom, the left 2 are the 1-month-old, and the right 2 are the 6-month-old. So you can see that there's a huge change in brain size and density of neurons, and that basically is what makes us us and smart. And so now we're going to look at something that's really neat about humans, plants, and insects, is that we all share common history as eukaryotes. So you don't really think about this often, but on the tree of life, we are pretty much the same. You know, plants and other things, like humans have been around the last 50,000 years as we are. And so like pretty much in evolution, plants have very, very little to do with humans until we start selectively breeding them much, much, much later on. But prior to that, insects were the main, insects and plants were on Earth for hundreds of millions of years. Plants alone were on Earth for hundreds of millions of years. Insects came out first, and so there was this kind of war waged with plants, and it's a symbiotic relationship with some other insects, which is basically the plants can't move, so they need pollinators. So they have bees and things like that to move the pollen from one plant to the other. And there's so many cool things about plants and insects and sex that we could get into, but we don't really have time in this talk. So what we're going to look at, though, is this balance between predators and insect omnivore predators and pollinators. So in this chart here, you can kind of see everything going on. Is that like the plant will release pheromones to draw insects it wants. What's cool is if it's being attacked, the plant sometimes, certain species of plants, they can release a certain pheromone that brings the predator to the thing that's eating them. So it doesn't have pollen for them, but it has their food is, hey, your food's here, eating eat me, come eat this thing. And so plants have developed a lot of different molecules to work in this exchange. So one we're going to look at is probably the most widely known cognitive enhancer, or well, also here we're calling a secondary metabolite, which is basically, its secondary metabolite is something that the plant makes that's not for primary use. So plants are autotrophs. Autotrophs can manufacture anything they want from their environment. And so that's what makes plants really unique, is that they can kind of just, they're like a manufacturing facility. But what happened in evolution is there was multiple times where plants duplicated their DNA completely. So just within their DNA, they have a whole second copy of all that functioning DNA, and then they had hundreds of millions of years for little variations to change, and that's where a lot of the molecules we're familiar with from plants come out. And so you have, through selection, you get things like caffeine, which was came about at least 5 times, different species, lineages. The molecule has a very strong self-selecting bias, and we're going to look at that, what that common lineage has to do with why it works in humans. It's not just about does it work or looking at the process, but we're going to look at that. And also, we don't have time to go into the individual things, but we can look at like certain drugs, like why does a poppy seed make opium? Like why would that be good in nature? But actually it's there to drug the predator that's eating it so that it just sits around and then it gets like picked off by a bird or something. It's literally like drugging the bug the same way we see that effect on humans. And so if you start to look at drugs like that plants make, you start to change your perspective a little bit about like maybe I shouldn't take that one. It's literally meant to eliminate you from the gene pool. Yeah, whereas like coffee is meant to stimulate the bee, to remind it of where it's going, and make sure it remembers that plant so it can come back and pollinate it again. And so we're going to look at this suite of molecules in how they're used in plants, and they're also used in humans. I believe we have acetylcholine there. So acetylcholine is basically it's in plants as well. That's the main neurotransmitter for memory. But in plants, it helps regulate their photosynthesis and all these other things. And we share these like common calcium-gated channels, the same signaling that humans use, plants use. And I don't know if we passed the slide because I can't really see them over there. But basically, we have like 22,000 main genes. We have 2,000 like housekeeping genes, these original genes that we share with the plants and with the insects. We all have this like core 2,000 genes that regulate the opening and channeling, our cellular communication, and things like that. So now Yeah, and there's like models of bee brains being mimetics for human brains, and bees can teach each other. Bees are actually really neat. We know about reward molecules like caffeine. So check out the shape of caffeine over there. So caffeine and adenosine are very similarly shaped. And so in this case, the shape has a lot to do with how it affects our brain. And so a little quick overview of caffeine and the way it works in us, and one of the easiest mechanisms to understand is that our body has this bank of adenosine. Every time we're awake, little adenosine molecules are jumping in our brain somewhere. So after we're awake a certain amount of time and we have a certain amount of adenosine build up, our body's like, huh, I'm tired, I'm going to bed. And that's kind of how our body regulates in a very simple way being awake, especially from that system. And so caffeine, if you look at the shape of the molecule, it's very similar to adenosine, and it just fits in the slot and it blocks the adenosine from being absorbed. And that's why your body on caffeine is not tired. There's other effects, but that's kind of like a very basic mechanism to understand. And because we're going to look at how coffee affects us. And here we're going to shift a little bit towards what these molecules have not only done in our brains, but what have they done for us as a society? How have they shaped us? What have they changed? And what have they made different? And so coffee is an amazing one because it comes from Africa. And there's a couple stories about a goat herder who sees his goats eating them, and let me try those berries. Or one guy who gets like sent out into the desert to be like expelled from society, discovers the coffee bean, sustains himself, and then comes back. And then the coffee was in the Arab world there in Africa, and it basically, I don't have the time to go into it in the slides, but it's banned, it's unbanned. They're like, is this an intoxicant? And there's a debate because they can't drink alcohol, and this is changing who you are. And so it's pretty much like almost snuffed out, but you can't stop coffee. And so someone sneaks out some plants to Amsterdam, and now coffee makes it to Europe. And so back in this is like the 1700s and 1800s, and back then, water purity, like they didn't really know about germ theory. The wells, there's like dead animals and bodies in the well, and they're drinking their water right next to it. But they knew that something in the water was bad and could get you sick. And so people knew that boiled drinks or booze that was fermented was safe, just from experimenting over time. And so basically, coffee had this effect. They call it the great soberer. And I love to do those quotes. I hope you guys can read them. But basically, one of them says, the lucidity of the mind. And another one talks about the, everybody basically, imagine if you're drinking fortified wine or beer, low-level alcohol wine or beer all day from when you wake up to when you go to bed. So everybody in this society, the accountants, everything, drunk by noon, by lunchtime. So imagine that the world in this version of it is, especially in like a city like London, where we're going to go a little deeper, it was a bunch of drunks, and that was that, and so there was like the dark ages kind of in a way. And so coffee actually you can make an argument that it fomented the Enlightenment, and basically the coffee houses became these central gathering points, especially in a class society like London at the time. Anybody could go into a coffee shop. They called them penny universities, and you could go in there, and they had little groups and different ones with people. Some people were studying astronomy, this one, and you could just go to that coffee shop and have all those people. You can have all those people there and discuss with them. And so you can like trace. Does that say Newton over there? Yeah. So Newton had a conversation in a coffee shop about gravity, and then when he went to Oxford, he picked that conversation up in another coffee shop, and that's how we got the theory of gravity. And so we have a number of these things. You can find like Diderot, Voltaire in the French coffee houses, and you can find like fomenting of like revolutions and people trying to shut them down. And if you look all throughout the history and you dig deep into the English history especially, you find like the first insurance market, Lloyd's of London. The stock market was originally called Jonathan's, and then they got in a fight and they made one called New Jonathan's. But basically that was where the first stock market started, because the businessmen could meet with the guys coming in from the ships, and it was a classless place where they could all interact, have ideas, and instead of going to like a dark bar and getting drunk, these people are like going to a coffee house and getting stimulated. And so we can see the positive effects of cognitive enhancers. Who in here has caffeine in their system right now? Okay, it's like 90% the statistic they say. And every time I'm like, that sounds a little high, but then everybody raises their hand, So it really is a drug that's prolific in our society, and it's kind of neat that it came from this like singular lineage out of Africa and into Europe and around. So we're going to move on here, and so what is that one? This is so now we're going to look at starting to get to synthetic molecules. And so if anyone ever tells you that fashion is worthless and silly and to waste your time on it, this is an anecdote that you can throw right back in their face. And so basically chemistry, up until like, this is in the like 1860s and stuff, it was kind of like a rich man's like gimmick, and it was almost like magic tricks they would do in like salons and parlors. And it didn't have commercial uses. It wasn't like pursued realistically for anything besides this kind of pursuit of science in itself. And so William Perkins was studying quinine to try to make a synthetic version of quinine, which is a cure for malaria. But he had a fortunate kind of lab experiment that yielded, when he diluted these coal tar derivatives, so like in the dark ash of coal, he diluted it and it came out like light purple. He was like, huh. And purple at the time was made by going in the ocean, getting mollusks, crushing them up, and then like this expensive process, and only the wealthy could afford purple. And so by pursuit of the color, he basically invented organic chemistry like for making drugs. And so what's even wilder is that if you look at some of these color-shaped molecules here, you can actually see like, now if you think of that coffee and adenosine back again, that there is like the shape of these molecules is refracting color or doing different things. And so what happened is they start to modify different colors. So purple, just like we have fashion trends now, we had them back then. And so like the Queen of France, she wore like a purple dress, and then everybody wanted purple. And so it was a boom time. But then 2 years later, purple's not cool anymore, and they're trying to come up with the next one. And so for red, they have like a race to the patent office between a few different groups pursuing this. And so they end up coming within a day of each other, and so they award it to both of them. And so at this point, they're like, we need to like do even more research. So they go to the universities and they're like, give me all your best scientists. We'll pay them. Just find us the next color. And this is actually the same drug development process that we have today, where companies sponsor university research and governments and other things in this this team drug development process. So we owe fashion a debt of gratitude because it helped us get organic synthetic chemistry. Okay, and so here we're going to now look at the negatives briefly of potentially, here's a positive one, we have a negative one coming up, about cognitive enhancers used for wrong, used for ill. And so fortunately in the Civil War, the North had coffee. It was actually in the rations, you were only guaranteed two things, coffee and hardtack. Hardtack is like an unleavened bread, kind of like a matzah or something. They would actually just like take that, dip it in the coffee and drink it, eat it, whatever you can call that. And there's stories about the fire, I took them out of here. So there's stories about like William McKinley went on a coffee run. He was a future president, and during the middle of the war, he like ran, as they called the most famous coffee run, and he used it in his campaigning in the 1800s. And he basically became president off of this story. And so we have coffee in the DNA of our country because we blockaded the South, and they didn't know of any other plants that had caffeine in them. And so they were like literally drinking mud, trying to find out like what's the essence of coffee. They had like plants, they would grind them. Imagine your morale if you had no coffee, and imagine in the fighting. And they talk about with McKinley that it's like putting in a new regiment when he did this coffee run. So we can see that like coffee shaped the war for good. And then, I think that's actually the picture of the coffee run over there. And so, so then we look at, I'm going to skip over there's a lot of war stuff because, like in terms of like surgery and operating on soldiers, at the beginning of World War I, we were like using hot air balloons, and when people were like injured, they would just like drag them to like an area off to the side, and they would just basically die. There was no surgery, there was no like medicine. It was very much like barbaric. But by the end of World War I, they had a hospital system, and they had all these things had come together. And so like war and the atrocities of it did push us forward. And there's an argument to be made about prosthetics, for example, like all the people being blown up, they now have a lot of money going into making much better prosthetics. So war, while it's terrible, it does sometimes have these like counterintuitive benefits. And so like, here's where it goes terrible. So there's a great book called Blitzed, and it's about the Nazis in World War II and how they were basically all hopped up on amphetamine. So amphetamine, like Adderall or different things like that, are not considered nootropics. Those are stimulants, and they, in a way, they activate your fight or flight response. So if you're at war and you literally want to fight, that's a great thing to have. But it did allow the Nazis to have an unfair advantage. There were like millions and millions and millions of doses of Prevatin to go on. And that book basically is like World War II through the eyes of Hitler's doctor. It's insane. It's like his journal notes. And he was getting injected by the end of the war with like bull testicle extract and all these 100 things. It's insane. Including, but he also did get addicted to cocaine, which also was another doctor that helped cause his downfall. And so we don't have time for that. So let's get to the good stuff. I also took out the stuff on neuroscience in the 20th century, but we'll talk real quickly about Kayal there. Ramonde Kayal is a neuroscientist who invented this method to dye neurons. Like some neurons are big enough that you could see them with a naked eye. And so all they needed to do was to be dyed. And so he said this thing about sculpting your brain. Where they say, man is so inclined, he can sculpt his own brain. So he has a link kind of to a guy named Penfield. Oh, I don't know where. Wilder Penfield. So I don't know what happened to the text because this came from Keynote. But basically, all that gold area there is what Wilder Penfield called the uncommitted cortex. So when we're born, our brains are pretty much, except for, we have a small area for sensory, but the rest of it is uncommitted, meaning we have the ability to shape our brain to connect it to whatever we want. And that's the process of learning, language acquisition, all that. If you look at the lower level animals, they have very little gold areas because their brain comes wired purely for sensory. So their brain is mostly about their eyes, about their ears, their nose, and what goes along with that. So they don't have a lot of room for critical thinking. And so, let's see. Basically, this is embarrassing, but like we didn't use the term neuroscience until I think 1963, and we didn't really even understand neurotransmitters that well until relatively recently as well. And so I believe it's like 1959, Ernst Fleury, out of a squid, dyed this neurotransmitter that would later be known as GABA. And it was basically the first time we discovered an inhibitory neurotransmitter. So GABA basically tells our brain, stop. Other neurotransmitters like acetylcholine and stuff generally say, go, go. And so they're like, huh, this is a molecule that lets us like stop the brain from being active. Maybe we should try to make a sleep aid. And so this I've taken out of this is a picture from the history written by Gurdjieff, the originator of the nootropic concept. So they're studying cyclical derivatives, and they find this molecule, and they have a bunch of tests they're going to run, and we're going to look at some of them. But there was one where it was active. It was a test for nystagmus, which is like an uncontrolled eye shaking. And one of the tests they do is they have a rat on a little thing, and they can see its eye shaking. And normally, up to this point, the only things that ever worked on the rat to fix that were antihistamines and anticholinergics. And so they knew that this was something was going on because it wasn't either of those classes of molecules. So like, huh, let's look deeper into this. And this is like where a good scientist with a good inkling makes a discovery that otherwise would have been overlooked, because they've got, this thing was called UCB 6215. There was a 6216 and a 6214. Similarly with LSD 25. That has nothing to do with the chemical structure. It was a 25th version of the lysergamides that they made. And basically, Albert Hofmann and LSD noticed that the rats in the cage were acting kind of weird because they were high as hell on acid. And so later on, like years later, when he went to revisit the lysergic acids he had, he basically was like, let's try that LSD 25 again. And then purely from a hunch and purely from being a good scientist, who then went on to take the molecule himself and took 250 micrograms and tripped himself out. And that's how he got bicycle day, because he had to ride home high on 2.5 hits of acid on a bicycle. That's true science there. We're going to get to the citizen science rate in a bit, though. So let's look at some of these unusual characteristics. So piracetam, what that molecule is the original nootropic. I love piracetam. It's amazing. It's a little weak, but that's part of why it was so difficult to understand it, because piracetam basically, it required like it requires multiple gram doses a lot. And basically, they're like, it's not toxic, even in like pounds they gave to dogs over 6 months a day. And they're like, this thing, how can it even be active? Because it's almost inactive on high doses. And so here's like one where they put an animal up to an EEG electrodes on its brain. This is the corpus callosum. So you can actually like see, this is the normal one. This is like after 15 minutes or whatever, but look what changes in the graph. You see the amplitude, the width of the graph, the height of the graph change. So piracetam doesn't really mess with your brain waves. It doesn't mess with them in changing the information thrown across it, but it increases the amount and the intensity of it. So what it's doing in a non-stimulant way is like increasing the amplitude of your activity. And it does a lot of really neat things. We're going to look at some kind of briefly. Here's one that really threw them for a loop, which was basically rats that they gave piracetam. They then suffocated them, and the rats on piracetam came back in 17 minutes versus, I believe, 31 or 33. What is that? Yeah, 30, yeah. So 17 minutes. So they basically came back double as quick. And so these are sort of tests that are mimetics for whether or not you had a stroke or something. Basically, the damage in your brain that comes from a stroke is a lot of times from the lack of oxygen. And basically, when your brain fires and it runs out of oxygen, your neurons will be like, oh, this is my last shot to release all the energy I have. And you basically like fry an area of your brain. There's no way to flip the circuit breaker back. So that's where a lot of damage to strokes comes from. So something with the nootropics and the racetams, they actually like keep the glutamate in the neuron instead of the synapse so it doesn't fry. So this is a cool experiment where they put rats in cages. Rats will always go to the darkest area. So they lock them in that little area. Then they flash a light on in the rest of the cage. And so generally the rat, if it comes back the next day, once it's locked in there, they shock its foot. And so it comes back the next day. It may go to that area, but if they turn on that light, it gets the heck out of that area. So what they do is then they electrically convulsive shock the brain of the rat in one version, and then the next version, they take out the oxygen. They suffocate it again. So normally, you'll see the stats here. There's like the first graph there, I believe, is that electroshock? I can't see. But basically, yeah, I think so. Yeah, so the first one, I think, is lack of oxygen. But basically, the rats, remember that second column there on the left side is like when they barely remember, like less than 20%. So then it goes all the way back up if they were given piracetam prior to being shocked or suffocated. I think this one is, so on this side here, you can see if they're given piracetam prior and then they lose the oxygen, they retain all of their memory pretty much, like they're not affected by memory loss, which occurs because after you form a memory, you basically have to process it into a longer term memory. And so the electric shocking or the loss of oxygen immediately after would normally cause you to not remember. And in this case, you can see piracetam. So they're very curious. They're like, what's going on here? And so this guy, the principal investigator, Cornelia Gurgia, the head of the lab, he decides to like go around to all the people who've made drug classifications. There's delayed Dineker system, I believe these are, at least the top one. And so he's like, like what could this thing be? It's not a stimulant, it's not a psychomimetics, by the way, were the name of psychedelics back then because they thought they mimicked psychosis, and they used psychedelics, psychomimetics, to test people for psychosis or rats and things. So you can see it didn't have its own area. So he's like, this doesn't fit into any known category, what are we gonna do? And so they talk about even in high doses, it doesn't have an effect, yet it seems to do this in enhanced learning. He decides to coin this term, a nootropic, from nous meaning mind and tropin meaning towards. And so, what is a nootropic? So this is basically the kind of isolated things where it does like, I don't know the order, but it's basically like, okay, it enhances, the middle one is increases interhemispherical connection, we saw that. We know, I think it has a resistance to amnesia and also things that would tend to mess up your memory. It can't be toxic, it can't cause an issue. And so, yeah, these are the properties there. It also has to like not affect a lower level brain function. So this is a part where you can easily draw the distinguishing between what is and what is not a nootropic. So things can have nootropic-like effects or be a cognitive enhancer. Like caffeine is a cognitive enhancer, but because it's a central nervous stimulant, it's not actually a nootropic. But like a cognitive enhancer could make you smart today, but kill you tomorrow. A nootropic has to be non-toxic. And if it causes damage or has really crazy side effects, it's not a nootropic. And so you can look at things like modafinil and other stuff and say, well, when your top layer of your skin falls off from modafinil, that might be a bad side effect that you clearly know it's not a nootropic. Or like, if your heart rate is beating out of your chest, that's not a nootropic. So just be careful when people try to use this nootropic term because it has a very specific meaning. Here's a really cool study where this is one of the first like human studies proving some of the animal effects. So this is called a dichotic listening test. So remember those pictures of the brain early on where you have the left and the right side? So our brain has specific regions like Wernicke's area and Broca's area, which are speech and language processing areas. And so if also you have to know is that our brain sensory stuff is cross-wired. So your left eye, left ear are processed on your right side of your brain. Your right eye, right ear are processed on your right side. So if you have a specific region that's only on one side of the brain, if you're left, usually these are all just determined if you're right-handed. If you're left-handed, it'll be opposite. But so if you're right-handed, on the right side of your brain, you'll have the Wernicke's area. So basically, sound coming in the right ear, I think I'm all backwards here, but sound coming in your right ear gets processed on the left side, and then to verbalize it, it has to transfer back to the right side to where you have Wernicke's area, Broca's area in this case. So when the people took Piracetam, and this is like a 2-week study they did, they had a 15% gain in more words remembered from that side. And so that's like part of what you could say, like what do nootropics do? Like is there a test? You can try to test stuff like this, but what I get feedback from people and what people say on the internet is, I feel like I just like have better language coming out, words I haven't said in years, I'm verbalizing and things like that. So I believe that that comes directly from the enhancement of interhemispherical communication, leading to like more ability to put words across to the other thing. So here's another study. This one was done in healthy college kids, 2 weeks again. This is called Increase, love this title of the study, Increase in the Power of Human Memory Through the Use of Drugs. And basically similar, this is a verbal listening test, and they found that healthy college students improved, the first test, no difference, second test, slight difference, but not statistically significant. Between 7 and 14 days, something happened where they came back and they were much better at recalling these words. So when you take a nootropic, don't expect it to work the first time. Even though we have EEGs that show changes in your brain waves, it does take time. And that's different than other classes of molecules where like every time you take them, they get worse, especially the more you take them. Whereas nootropics, as long as you don't overdo it, generally like get better over time within reason. So, okay, perfect. So then we're going to look at some synergies. If we have time for questions or other formulating stuff, I'm happy to go into with you guys. But basically, part of the way we know the nootropics work is they affect the cholinergistic system. And so one thing is if your cholinergistic system is not running smoothly, you may have all these other deficits that the nootropics can't necessarily help. And even if you're healthy, and you still may not have all the materials and things that your brain needs. And so by adding choline alone, you can like have some effect. You can see that on that like the third to last column on the right there. And if you're but if you take choline and piracetam together, they have this profound effect. So when you combine the two, they work a lot better. And so that is the basis of the nootropic stack, is a nootropic in the racetam class plus a source of choline. I like acetylcholine because it has membranes on it, it has methyl donors, so it helps your body in a lot of other ways that you may be short on. And so there are other ones like alpha GPC, there's extracts from sunflower seeds, soy seeds, sunflower seeds, and other things. So find a source of choline plus piracetam. So now we're going to look at the science real quick, and basically this is the increase in interest of the term nootropics in PubMed's database over time. So we can see that even though the nootropic concept was coined in 1972, that interest has been increasing. I like to call this like the second wave, where the first wave was the science mostly in Europe, and they got it took half a decade to get approved, and then it was on the thing. If you look, like you can find in the 70s and 80s in the German like medical thing, the term nootropics is listed, but they eventually removed it because there's a lot of debate about what do you give to somebody who's aging or like getting older, and basically the idea is that those things don't necessarily work as a savior to somebody who has dementia, although there are all studies showing you can at least prevent further decline with piracetam. So here's a bunch of studies where they like went over this for decades of research. There's some crazy studies there about for example, piracetam for babies in the womb, where they're like, if you're having trouble, premature baby, and it's stuck, instead of doing a C-section, could you give the mother piracetam, which will get into the baby, into the fetus and the baby, and then prevent the lack of oxygen from that? So they actually found the results were better than C-sections. And so this is just some of the other data saying, let's move from the question of does it work, and to see where can we apply it. And so when you use fair metrics, you can find you can find a significant improvement in most of the population most of the time. But sometimes if a drug works on 50% of people, that's not good enough. And so, but they don't work on giving choline, they don't work on changing their diet. So there's other ways you can modulate whether nootropics work, and many times studies don't do that. But what's cool is that so this is the racetam family. Piracetam's in the middle, and they've added on different molecules. I like one called phenylpiracetam, which is piracetam plus a little phenyl group, and it's more stimulating. Anoracetam's a great one. It's calming, creativity boosting. It's fat soluble. They all have different properties. It's kind of neat. Noopep is also a really good one, which is a Russian dipeptide version of piracetam. That's where piracetam you need 10 grams. Noopep you need 10 milligrams. So it's 1,000 times stronger by molecular weight. And that one's awesome. It's in part of my product. So this is a cool one. This is, I think, one of the last slides. So this is a story that kind of harkens back to where I found out about nootropics, which was basically in the internet forums. So in this second wave of nootropics, we're seeing the research being done by citizen scientists. There's on subreddit, our nootropics. There's a forum, Longicity. You have people experimenting, going into the scientific papers, finding molecules that were abandoned for whatever reason. And then there's a great molecule here, basically that it came about by a guy in Italy at University of Florence was studying. And this is in 2007, 2008. He finds this molecule. He does a bunch of tests on it. And the economic collapse comes, and they shut down his funding. And so years later, 2011, I think somewhere around there, he's sitting at his desk, he gets an email from a guy, hey, what do you think the dosing is for this? He doesn't respond. He's like, I don't know. Months later, he gets a email back from the guy, says, okay, I tried it, it's great, this is the dosing I'm using. And he's like, what the heck? How did you get this molecule? And he goes and just does a search, and it's all available, sold by mini sellers from Alibaba and on the internet. And so he's like, what the heck? And it kind of goes back and forth. And so he's like, man, if only we had the money, if only the university had paid for the patents and all this stuff. And he says, I would have not only made money on this, but we could have had a new drug for the world that was backed by everything that's required to make it clinical use. And it's sad. But the good news is we don't have to worry about that kind of thing as much, because the citizens will find the molecules. Science will win. Kevin Kelly believes that you can't, a futurist, basically says you can't stop a technology, you can only delay it. And so these molecules will come out, and so the people in the internet, they're pushing the frontier forward and maybe making the scientists up their game. It's if you don't do this, we're going to do it. And so you see citizen scientists doing it and trying to do it responsibly, but the idea is that science will push forward, just like evolution, just like everything has. And so yeah, I think that's the last slide there. And yeah, so thank you guys. That's normally a much longer talk, so I tried to speak a little faster for you guys. I hope it was palpable.